Okay, well, allow me to introduce Timur Doumler. Timur, I've known Timur for a very long time. He first studied physics and did astrophysics, right? And then he worked a while at NI after he realized you can't really earn any money doing astrophysics. And then he worked with me and the Juice team for a long while. And then worked on the Sea Lion team, was developer relations there, and now you're a contractor and doing odd bits and pieces of work. So put your hands together for Timur, and excited to hear what he says about atomics.
Thank you. Is this thing on? How do I?
It's just recording. So.
Oh, it's just recording. So it should be fine, yeah?
Yeah.
Can you try to say something?
Hello, hello, test, test. Okay. Thank you very much for having me at your first meetup. This is very exciting, of course, when there's a new meetup. Like, super cool. I also grew up here in Berlin, although I don't live here anymore, so it's very special to see a meetup here. Thank you so much, Fabian and Rachel, for organizing this and inviting me. It's very, very cool. I have a little talk about state memory order. And this actually also goes back to a conversation I had with Fabian, because I did a talk about the seq log, which is a particular log-free algorithm, at the Audio Developer Conference in the UK in November. And I had a mistake on my slide. And Fabian was like, oh, but that's not quite right the way you explained that here. And I was like, oh, okay, it looks like I don't quite understand it. So I kind of figured it out, and then I decided, okay, I really need to give a talk on this, because quite a lot of people are confused about this topic. What I want to do is I want to talk about state memory order, what it does, what it's for, how to use it. Kind of very brief overview, because I don't think I have time for a long talk here. So just to set kind of the setting, I think this is something that should probably be familiar for people who do C++ and audio, which I think most of you are, right? Yeah. So we kind of have one thread, which is this real-time processing thread, which must not block, otherwise you're going to get an audio glitch. And we're going to have a bunch of other threads that are not real-time threads, that are doing other things like rendering your GUI or media I/O or whatever. And you want to share data or move data between those threads somehow, without blocking the real-time thread. And that invariably involves, you inevitably end up using things like log-free algorithms and log-free data structures, and there's a bunch of them. And Fabian gave a few wonderful talks about that. I have a few talks about that too. So there's like the cast loop, double buffering, RCU, seq log, that was my most recent one. Log-free queue, which I think a lot of audio people will be familiar with. So all of that stuff, I'm not going to talk about all of that, because there's a bunch of people who've done these talks. I'm going to talk about the building block that you need to build all of these, in C++ at least. It's state atomic. So who's familiar with state atomic? Right, that's almost everybody in the room. That's good. So as you all know, it has kind of this interface, right? There is load and store, which is kind of like read and write, and then there's a bunch of read, modify, write operations. And then they have these like shorthand notations, right? So they have a bunch of kind of operators that are defined there. So for example, instead of like writing load and store, you can just assign basically, and it's just going to do the same thing for you. And instead of doing fetch add, you can just fetch add 1, you can just increment. That's kind of a short version. However, it's actually not a good idea to use them. That's why I kind of grayed them out here. I don't recommend ever using that short form. I think you should always write out like the function name. The first reason is to make it obvious that that's an atomic operation going on here. And the second reason is what you're going to talk about now. This is, I think, like kind of the classical first example. You have, gain knob, and then you have these two threads, right? You have like some kind of audio plugin. This is highly simplified, like slideware code. So you have one thread that kind of reads the value of the knob from the GUI and sets the gain, right? And you have another thread that produces the audio and multiplies all the samples with the gain, right? So that is kind of the simplest audio plugin you can build. And of course, there is a bug here. What's the bug?
Gain isn't atomic.
Yeah. So there's a data race, and that's undefined behavior. Can't do that. So you need to make this atomic. And now this is going to compile. So now we're using these short forms, but it's better to use the long form. First of all, as I said, it's obvious that we're using an atomic, but more importantly, if you use the long form, you can give it a second parameter, which all of these atomic operations have an extra parameter at the end, which is the memory order, and you can specify it. And that is actually really important because this is how you kind of make your algorithm or whatever you're doing with these atomics both performant and correct. And if you're not doing this, then you're probably not doing it right. So we're going to talk about state memory order for the remainder of however much time I have. What the problem with memory order and why it took me a while to like wrap my head around this, and I think why everybody else is I think struggling with it too, is because anytime you read about memory order, you just like on CPP reference or wherever, it's usually just this is how this is specified, and then there's just a wall of text, and it's like really complicated, and it doesn't make sense, and it's very confusing. So what I don't want to do today is to repeat that. I don't think that's very helpful. What instead I want to do is I want to get across the general idea, like why is this there? What is this for? And what problem is this actually solving? And then give a little bit of an overview how you use it and when, but not to go into too much detail. So kind of gloss over the details a little bit and just give you a general idea. But then if you do want to know all the details, you can then read the actual specification, and hopefully that will then make more sense. So that's kind of what I want to do. Like if I were to explain this properly, it would be like a one-day workshop. So we don't have time for this, but I think just getting across the idea what this is for is really important. And to understand why this is there and why we need this, we really need to understand, why this without the atomic, why that's undefined behavior, and why that's bad, right? So what is the actual reason for this? And so, you might say, well, it's undefined behavior, so anything can happen. So, there could be a dragon emerging from, your screen and putting your laptop on fire when you run this code. And according to the ISO C++ standard, that would be conforming behavior, right? That's standard compliant behavior because you have undefined behavior. The standard poses no restrictions on what your program is going to do. But of course, in real life, you're not going to have a dragon probably emerging from your screen. And so why is this a bug, and why is this so bad, and what's actually happening there? Because on the hardware level, on most modern architectures, like what we do probably in kind of at least with a lot of the music software, it kind of runs on laptops or phones, so it's probably Intel and ARM. And on those architectures, there's no magic atomic and non-atomic instructions, right? There's just loads and stores. You're just reading and writing bytes, right? There's no magic around this. So why is this still a problem? And so there's a bunch of reasons. One is the compiler. If you have an optimizing compiler, which you do because you want your code to run fast, it can reorder stuff, right? You can reorder operations. You can elide operations if it can prove that something happens that it doesn't actually need to do that. As long as the observable behavior of the program is the same, and by that I mean the I/O, like the file output or std out or whatever you're writing and reading, as long as that's guaranteed the same, input and output, the compiler can do pretty much anything to your program at once. That's the as-if rule, right? So it can reorder any operations or just optimize them out of existence. And when it does that, it assumes that no undefined behavior ever happens. So that's what undefined behavior really is. It's not an error. It's not like, oh, you did something evil, I'm going to punish you. No, it's like the compiler is going to assume that that can't happen and optimize based on that assumption. So one of the assumptions is if you have a non-atomic variable, then you can't have a data race because that's undefined behavior. So no other thread is going to read from this or write to this. So all of these optimization where it's like reordering is not taking any other threads into account. So if you then do have another thread looking at that variable, it's going to see things written in the wrong order or not see updates of the value at all and things like that. But it's not just the compiler. Actually, even more importantly, this happens on the hardware level as well, right? So the modern CPUs, they have all kinds of hardware optimizations, right? They have instruction reordering in the hardware. They have pipelining where you have like multiple micro instructions happening at the same time and all kinds of weird stuff. And that also assumes that, there's no other thread that will be looking at this. And the hardest one of these is when you have multi-core systems, which we all do these days, and they have caches, right? And so So you typically have an L1 cache, which is per core, and then you have maybe an L2 cache, which is shared between multiple cores, and then you have maybe an L3 cache, and then main memory, which is shared between all the cores. And how do all of these multi-level caches that are kind of shared between cores or not, how do they communicate between each other? How do they make sure that if one core writes something into a cache and then another core reads from like his own cache, the same cache line, and then they have a shared cache above them, how do they agree on what the value is, right? So that's all implemented in hardware. That's very, very complicated. That's typically proprietary stuff that like nobody really knows how it works apart from the people who build it. And that's also vastly different between different architectures. And so that stuff also leads to all kinds of things, including the fact that different threads can observe operations like values being written into pieces in memory happening in a different order, right? So one thread can see A is written before B, and another thread can see the other way around. Or maybe the third thread doesn't see any operations at all. This is just a consequence of this kind of architecture that we have these days. And so what we want to do here, if you're writing log-free code, is you want to tell the compiler and the hardware and the machine that our code is running on, okay, but please don't do all of the stuff here because that's going to break my algorithm. Please, don't do this and this and this because otherwise my algorithm would break, because my algorithm relies on the threads agreeing on what the value of a variable is, right? And so there's different ways you can do this. Kind of the most primitive one is just std atomic itself. If you use that, you're telling it, well, don't assume you don't assume that no other thread is reading or writing to the same variable. That's what atomic is for. But it's kind of not enough granularity. It's kind of enough granularity to get correctness in some cases, but not enough granularity to also get performance. And the other extreme would be to be able to tell the machine very granular, like, don't do this cache coherence protocol for this case, and but that's not portable, right? So because those things are very, very different in different machines. So kind of what you want to do is you want to have an abstraction level which kind of gives you reasonable options that cover most use cases, which sit on top of all the different architectures doing all of these different things, and give you some kind of abstraction layer that lets you express things that you can express to make your algorithm correct. And that's what the CSS memory model is. And those different options for expressing those things is what this is for, right? It's for basically it's picking certain particular aspects of what the machine is allowed and not allowed to do in a way that is useful for many use cases. So that's basically the purpose of this. By the way, this is really informal, I think. So if anybody wants to interrupt because they have a question, you can just do that at any time. That's not a problem at all. I think we're gonna have the mic being thrown around. So if anything's not clear, just shout. We have. Okay, so this is what this is for. This is the idea. And how do you express? So basically, when C++ 11 was developed, this is when this was developed. People came up with a certain set of options that covers kind of most use cases. And those options are the 6 possible values for memory order that there are. And so 6 options sounds a bit scary, but it's actually not that scary because one of them isn't really a thing. So the memory order consume is something that people came up with. Turns out this is not really how hardware works. Can't really implement that in hardware. It's not really useful. So no compiler ever implemented this, and we're actually going to deprecate this in CSS 26. So just pretend this wasn't there and never use it. So we're left with 5. That's already better. But it turns out it's actually even easier because really it's just 3. So the first one is relaxed memory order. This is the first one. The second option is acquire release memory order, which is those 3. And acquire goes on all the load operations, and release goes on the store operations, and acquire release goes on read, modify, write operations. But it's kind of the same memory order option, so to say. So that's kind of option 2. And then option 3 is sequentially consistent, which is the default, but almost never what you want to actually use, which is why you should always use the long form and specify what you do want to use. So we're going to talk about that last. You're going to start with relaxed. And some people say relaxed is actually complicated. I don't think that's the case. I think relaxed is actually the simplest one. So I'm going to start with that. So we said that, the machine can reorder anything anywhere, and this is just like how this works. And so these introduce restrictions on that. And relaxed is kind of the least restrictive and the most performant. And sequentially consistent is like the most conservative, the one that introduces the most restrictions, but that also slows down your code the most. So if you care about performance, you want to use the optimal one, the one that's restrictive enough that your algorithm is not going to break, but not so restrictive that it's going to be slower than it should be. So relaxed is the least restrictive one. And what relaxed does is that if you have access to one particular atomic variable, let's call it B, then relaxed atomic says that can happen concurrently from multiple threads. So if you use relaxed atomics, you're not going to have a data race. You're not going to have undefined behavior. And it's also guaranteed that accesses to this one variable, like all the threads are going to agree in what order they happen. But it doesn't impose any memory order on any other operations on any other variables, whether they're atomic or non-atomic. So for this one atomic, all the threads are going to agree on the order, but it doesn't say anything about anything else, and it can still be reordered in whichever way the machine wants. So that's relaxed. And this is really great when you are using operations on one atomic variable that doesn't depend on anything else in your code. This is when you use relaxed. And the classical example is, again, this from the beginning, when you have a single atomic and you read it from one thread and write that from the other thread. And it doesn't really interact with any other stores or loads or memory operations anywhere. It's just about that load on that variable and that store on the same variable on the other thread. Whenever you have a situation like this where you just really care about this one atomic in isolation and you want there to not be a data race on that, that's when you use relaxed. So that's what this is for. Some people say that relaxed somehow means that the other thread is going to see the value later or something. That's kind of a bit of a red herring. Like, none of this is about when things happen. Like, this is not what this is about. It's just about, like, when is the machine allowed to reorder things or to not reorder things. This is what all of this is about. Right. Anybody questions about relaxed so far? There's a question here.
This one thing always made me scratch my head, which, I mean, when you read the text, you can kind of figure out what to do, but clearly you need to also have a different policy for both stores and loads, and here you're using the same for both.
Relaxed is the same for both. The next one, you're gonna see something
then for
else.
the others, there's
for relaxed, it's just relaxed. For loads, for stores, for compare exchange, it's just relaxed. If you don't care about how this interacts with other stores and loads to other memory locations, you just care about this one atomic, everything's just relaxed. And it just works. And all the threads will agree on what happens to that one atomic and in what order, but you don't get any other guarantees beyond that. And here's a case where this breaks down. So let's say you have, and this is a pattern that I think kind of appears like this in many log-free algorithms. You have some data that is being written, and then there is a atomic flag that says the data is now ready, and it could be an audio buffer or whatever. So there's a flag that says this is now ready, and then the other thread spins on that flag, and then whenever the flag becomes true, it says, oh, now the other thread is done, and now it reads the value. Right? This is a really common pattern. And so what's the correct memory order here? So if you put relaxed here, right, I'm going to now using enum, so I don't have to spell out std memory order, : everywhere, but you know what I mean here. So is this okay or not? So remember, relaxed means all the threads are going to agree on in what order operations on this atomic are going to happen. But there's no restrictions on how, like on the relative order between operations on this atomic and anything else. So everything else that's not talking about this ready flag can still be reordered in whatever way by both the compiler and also the machine and the caches and all of that weird stuff that's going on there. Which means that write to data there, so it's not really just reordering, but it's more about like in what order do the other threads see that happening, right? It could be that thread 1 actually performs things in this order, but because of the way the cache works, thread 2 is going to observe it in the opposite order. So the thread 2 will see the code on the left as if data equals 42 was down there, right? As if it was the other way around. And that's allowed because relax doesn't impose anything on the order of this other variable there, data, right? So the thread 2 could be seeing it as if it was down there, or it could also be the other way around, that thread 1 sees the assert as if it was up there. And that means you have undefined behavior again, right? Because if thread 2 could observe the data right on the left as if it was below the ready store, then that's a concurrent access, right? So that's again undefined behavior. So even though you're using atomics here, right? Because you use the wrong memory order, it's too relaxed in this case, right? It's not restrictive enough to make this algorithm work. You can fix the undefined behavior by making the data also an atomic. So then you're not going to have UB anymore, but it still can reorder this, right? Because the relax doesn't say anything about the relative order of reads and writes to ready and reads and writes to data. They're like completely independent. So it can still swap them around in both threads, and so you can still get the wrong answer. So this is not UB, but this may still fail, this assert, right? Or it may fail on one thread and succeed on another thread. Or it may sometimes fail on one thread and sometimes not fail on the same thread, like depending on what the caches are doing and what the CPU is doing and whatever, right? So relax is not really the answer here. Whenever you have like a dependency between, like there's a flag or some other atomic operation on the one atomic, and that depends on other things, you use this one here, the acquire release one. And now I have to talk a little bit about the C++ memory model. So we are now, after all, going to look a little bit into how this is actually specified, but I'm going to keep this brief. So this is now from the C++ standard. So there's this concept that two expression evaluations conflict if one of them modifies a memory location and the other one reads or modifies the same memory location. So that means, what one thread is doing may affect the result in the other thread, basically. And then the execution of a program contains a data race if it has two potentially concurrent conflicting actions and one of them is not atomic. This is exactly the case when you get UB, and neither happens before the other. Now that's kind of something that means something, like this happens before is a special word of power. And whenever you get that, that's undefined behavior. So that's how a data race is defined in the standard. And so what does this happens before mean? So an evaluation A happens before an evaluation B if it's either sequenced before B or synchronizes with B, and then it's also transitive. So what does that mean? Sequenced before and synchronizes with. So sequenced before, that's the easy one. That's kind of intuitive. This is the specification. It basically is the relative order of operations within the same thread, right? So if you have, something in one thread and then something else, like lexically in the code, comes after it in the same thread, then it's sequenced after it. So for example, here on the same thread we call F1 and then F2, and so the call to F2 is sequenced. Yeah, the call to F1 is sequenced before call to F2. In most cases, if something appears before something in the code, it's sequenced before it. There's a few exceptions, like when you pass arguments to a function, then they are indeterminately sequenced. So like you don't know which argument is sequenced before which other one, like the initialization of the argument. But there's still a sequence, right? But if you have things in different threads, then they are not sequenced with respect to each other, right? So F1 and F2 here, because they happen on other threads, they're not sequenced with respect to each other. If you want to talk about the order of things across multiple threads, that's when this second concept comes in. A synchronizes with B. So, and now A and B are on different threads, so that's that case here. And an atomic operation A that performs a release operation synchronizes with an atomic operation B that performs an acquire operation on the same atomic, okay? And then we have this memory order release, which is a release operation, and memory order acquire, which is an acquire operation. That sounds complicated. Let me make this easier. So in this case, if we now use release and acquire, So remember, the release always goes in the store and the acquire always goes in the load. Then this release synchronizes with this acquire because they are on the same atomic variable, right? Same atomic flag. So a release always synchronizes with an acquire. And what that means is that everything that comes after the acquire is guaranteed to see everything that comes before the release, right? So if that load observes the store, it might not have happened yet. But if the load observes the store on the other thread, then it will also observe everything before it, right? So what this means is that if you have some other operation after the store, it might be reordered upwards, that's fine, but you can't order this down. So this acts kind of like an optimization barrier, both for the compiler but also for the hardware. So that data equals 42 is guaranteed to be observed before the store on all other threads. And on the other side, you have the symmetric situation. Nothing can move down, but this could move up. But that's fine, right? So with this guarantee, you know that there's no data race, because whenever ready load is true here, then you know that on the left the store has happened, and then you know everything before it also has happened. So you will always observe actually that data is 42. So this code is both not undefined behavior and also correct. So there's no bug, and also the assert will always hold. And that's how you use a reason acquire. Question?
Timur, did I understand it correctly? You said that the assert can move up, because if the assert can actually move up past while, you can read some other value which was there before 42.
So assert cannot be moved up.
Cannot. I thought you said can.
Right.
Okay,
so
sorry.
Again, on the left-hand side, stuff that happens after the release can be observed as if it happened before, but like stuff cannot move down a release, and stuff cannot move up an acquire. So it's kind of the other way around. Does that make sense? And this way you get this guarantee here that everything that happens after the acquire sees everything that happens before the release. So it's like symmetric. Does that make sense? Right. So this is release and acquire. There's no data race. Everything's great. There's one more detail. Sometimes when you have many atomics in flight at the same time, you want to use something that is called fences. And I'm just going to give a very quick example of that. Are you good? Do I still have time? You started at 15:15, right?
Yeah, that's fine. You're good. You're good.
I need like at most 10 more minutes, probably less than that. Are we good? Okay. Okay. So here's an example that I got from Fabian actually just before this, because the example I had wasn't really that good, but Fabian gave me a better one. Thank you very much. So this is from one of his talks. So here we have a log3 FIFO, and it doesn't really matter what this does. Like, let's just focus on like the atomics here. So we have again the situation where we have a release and an acquire. So this is like an exchange. So it's like a read and modify write. So it has an acquire release. Don't worry about that. So we have a release on the left that synchronizes with an acquire on the right. But actually what we're doing is we're writing lots of atomics in a loop, right? Both on the left and on the right. So this is correct, but it's going to be very slow, at least on some architectures, because you have potentially like a whole buffer, right? So you have like 1,000 atomic release operations on the left and 1,000 atomic acquire operations on the right. On some architectures, that's going to be very expensive because, again, the more restrictive they are, the more performance penalty you pay. So what you can do instead is you can use these fences. And so what they do is basically they, it's just one synchronizing operation instead of 1,000. And it's not tied to a particular atomic. But what it does, so the fence always synchronizes with the acquire on the other side. So the fences synchronize with each other. And they kind of, like the release fence kind of upgrades all the relaxed atomics before it to release atomics. And the acquire upgrades all the atomics, the relaxed ones, after it to acquire atomics for the purposes of when the threads see things happening. But without actually inserting these expensive instructions like a million times for every single atomic. So fences are really good if you're working with like lots of atomics or multiple atomics. You have an algorithm that has 3, 4, 5 atomics and they all have to synchronize with each other. You can kind of batch synchronize them this way by just putting fences in the right places. Okay. Yeah, question. Why would you have the buffer as atomic? Watch Fabian's talk. The idea is that there's a FIFO, and like on the left, it kind of what does it do? It kind of overwrites old data, and on the right, it like reads 0 when it's empty or something, whatever. It's a peculiarity of this data structure. Fabian's talk explains it all. What's your talk called?
I don't know, confessions, something.
Yeah, a real-time confession. So I just want to focus on the fences here and not on like the data structure. Okay, so this is acquire release. Very quickly, the last one, sequentially consistent, which is the one that is the default, but I have actually never had to use in my entire career. I've never seen a use case in real life where you actually need that. And it's also the most expensive one and the most restrictive one and the least performant one. And so what this does is, if you have sequentially consistent atomic operations, they're all observed, all the operations, all the atomics that have this sequentially consistent on them, they're observed in a consistent order on all the threads, right? So that's kind of the most restrictive one where like all the atomic operations are ordered. But that's actually on some architectures really expensive, right? So you probably don't want that unless your algorithm actually requires this. Most algorithms require just the acquire release, that's enough, like 90% of them. And I have never actually encountered a case where you need this extra guarantee. I found one on CPP reference, which involves 4 threads. So there's 2 flags, X and Y. The first thread sets X flag, the second thread sets the Y flag. Then the third thread, if the X flag was set before the Y flag, increment Z, and the last thread, if the Y flag was set before, so the other way around. If the flags were set in the other order, then it increments Z. And you want to make sure that Z is incremented by at least one of those 2 threads. And so there you need a guarantee that thread 3 and 4 observe these things in the same order always, even though they're different atomics. And that's when you need sequentially consistent. You have something like this. It's, I think, quite rare. There are some algorithms that require that, but almost always that's not what you want. And if you use that, you're going to pay a performance penalty.
So am I correct in understanding that somehow per process, the program needs to register all the atomics in the entire process that have this policy and then make sure that they're all properly synchronized?
No, that's not how it's usually implemented. This is an abstraction. What actually happens on the hardware side is way more complicated.
Okay.
I had a question to the previous slide. So you had their acquire release for the exchange. And is this for the needs of the algorithm or solely to make the exchange result visible to the other thread? That was confusing to me.
It's about making everything above it
No,
visible.
the previous one. Before. Yeah, so you have acquire release on the right. And is it in order to make just the exchange result itself visible to the other thread in time? So kind of it's not really like relaxed. It doesn't make the exchange value itself automatically visible. Or is it for the needs of the algorithm?
Do you want to take that question, Fabian?
Something about the algorithm.
Oh, okay. It's just about the algorithm. It's not.
Just imagine it were an acquire.
So for normal exchange, there could have been acquire, like in some other algorithm. Okay. Yeah. Thank you.
Right.
Because it scared me. Okay.
Right.
Thank you.
So actually, I want to say a little bit about your question, like the last one. So it's not about registering things. It's more about if a core writes something to memory and then like it actually writes it into its cache. But if it's sequentially consistent, then it needs to know that it needs to publish that to all the other cores. So then it's going to flush the cache, and it's going to have to update the higher level cache, the one that's shared, and that's going to take more time. So it's more about these like caching, like coherence operations that are happening, and they are very expensive, right?
It's done by side effects instead of registering.
Sorry?
It's done by the side effect of how to flushing the caches.
It's done via the cache coherence algorithm that's implemented in your compiler architecture. And what it does, like it has different flags for, is this cache line still valid? Is it like exclusive? Is it shared? There's like different states, and like on ARM it's different than on Intel. It's complicated. We can talk about it later. But it's that kind of stuff. I hope you get a general idea what we're talking about. Okay. Actually, this is my last topic. Differences between hardware architectures. It turns out that there's actually quite a lot of them, not just with the finer details, but even just with how they map to this model. So we have basically these this set of 3 possible memory order options, right? So relaxed, that's the fastest one, that's the least restrictive one. Then we have acquire release, which is kind of this middle ground, which seems to be the best choice for most algorithms. And then sequentially consistent, which is like the most restrictive, kind of the safest, but also the slowest. And you actually have this for reads and writes separately, right? Relaxed, acquire, sequential consistent, and relaxed release is sequential consistent for writes. And it turns out there's different kinds of architecture. So the 2 most popular ones are probably Intel and ARM. So on 64-bit Intel, that's called a strongly ordered architecture. So there, like a lot of this is imposed in hardware, right? So atomic loads on Intel 64-bit are always sequentially consistent. So you get that for free. And atomic stores are always release, right? So that means if you got, remember the very first example where I used relaxed and like that was wrong, you get a data race. On Intel, you just automatically get sequentially consistent loads and release stores basically for free, even if you wrote relaxed. So on Intel, you almost never run into these bugs because that code would just still work. And then you compile the same code on ARM, and it breaks horribly because ARM is a weakly ordered architecture, and there all atomic operations are relaxed by default. And if you write something that's stronger than relaxed, then it has to, like the compiler has to insert like manual, like fence instructions to make it work. And that's why on ARM you have a quite significant slowdown when you go like down this hierarchy, whereas on Intel, most of the time, it doesn't really matter what you write there. It's just all compiles down to normal reads and writes, right? So there's a big difference here between architectures. So yeah, I think that's actually all I have. This is my takeaway slide. So when you implement log-free algorithms, understand the memory model, understand memory orderings, at least superficially, like what I presented now. You can obviously dive deeper. Actually, there's a lot more guarantees. There's like guarantees about when you have 3 or 4 threads that some of these give you that I didn't explain or show examples for. But this is kind of the general idea. It goes deeper than this. But understand at least this. Always use the long form. Always actually write the intended memory order because that forces you to think about the algorithm and what the algorithm actually requires. And that also gives you the best performance. Use relax whenever you're dealing with a single one atomic in isolation. Use sequentially consistent whenever you actually need full sequential consistency, which is almost never. And so you kind of end up using acquire release most of the time. And always actually measure. That's really important. And that's not really the takeaway. The takeaway is don't do any of this. Like, just use a library. But it's good to be aware of how this works. Yeah, that's all I have. I just have, as a very last thing, I have a couple book recommendations if you want to know more. Obviously, you can find stuff on the internet, but if you're old school, you like reading books. There's 2 that I want to point out. One is the C++ Concurrency in Action by Anthony Williams. That's kind of the classic. It's very good to give you a foundation of how concurrency works in C++. It's kind of a bit dated, but still very good. And then this one, which is a much more recent one, which is not even a C++ book at all. It's a Rust book. But it's not really a Rust book. It's a book about low latency concurrency, which happens to have examples written in Rust, but that doesn't really matter. Like, you kind of figure it out because the memory model in Rust and C++ is the same. And this book contains by far the best explanation of the memory model that I've ever seen anywhere. So I think if I were to point out one book that helped me really understand this stuff in C++, then it would be this Rust book, actually. So read it. It's great. And that's it. Thank you very much.
Thank you, Timur. Do we have any last questions before we take a quick break? I don't want to throw this the whole way across.
My question is, do you have any advice on testing and checking if you actually got your code right?
This is the question I always ask when somebody else gives talks about this because I also don't know. I haven't heard a good answer yet. So if you're like an academic person, for some of the simpler algorithms, there are ways to like mathematically prove that they're correct. That's horrendously complex unless you're a mathematician. I guess the best advice I could give is use thread sanitizer and run it as many times as possible in as many different like ways as you can think of. Yeah. And you can do a little bit more. You can sometimes write unit tests. I've done this for one project, where you have a particular algorithm and you just inject kind of these, wait for this other thread here in like lots of places, and then you try all the different permutations. But it's very, very difficult to automate that. There used to be a tool that does it, but I don't think they make it anymore. It didn't quite work. This is very hard. Like I think we as a community haven't really figured out how to do it well. So yeah, just test it as much as you can.
Thanks.
Okay, with that, I think we'll take a 5-minute break.